Hello, AP Calculus students of the future. It's Mr. Ford here with another summer packet tutorial. This time we're looking at topic E, which is one of the ones that will save you a lot of time, very useful, and also very easy. Function transformations. We're going to take a minute to review this really quick, but for the most part, you probably will recognize these problems right away. Our CPM curriculum that we use does a lot of stuff with these, and in calculus, you can often shortcut your way through a lot of problems by recognizing how one function relates to another. And we'll be talking about that a lot. But for the most part, let's talk about the general kind of H-cave movement that we expect to see, or, I hate to use words expect and should when it comes to math students, especially ones I really haven't even met yet. So f of x could be anything, and usually it's what we call a parent function. In this particular case, I suppose it is the graph of x squared minus 1. That's your parent function. But for the most part, there are some basic rules about how you can transform this graph. First of all, if you take f of x and you add a k to it, usually we use the letter k for this. It could be any variable, doesn't matter. But this will cause the graph to go up k steps. And if k is a negative number, it can go down. So it might be worth mentioning that the word down could be used here also. Now, if we add or subtract a number 2x inside of the function before adding k, notice how in this case, what's important is that k is happening after the fact. We run our function, we get our answer, we just add k to it. Makes sense that would move the graph up or down a few steps because you get the same graph but moved up. Now, if we add or subtract a number inside of this before we run the function, we usually write x plus h here. This is important. Actually, more generally, I guess we usually write x minus h, because this one usually works a little backwards than what you might expect. In this case, it moves it to the right h steps, like this. And I did write that correctly. It goes to the right. If you subtract h, it goes to the right. If you add it, it goes to the left. This is probably the most common transformation that you'll see, and usually we write it all in kind of one fell swoop, kind of like this, in which case we say that it's been moved, or I guess moved is kind of a baby word. The big kid word would be used translated according to h comma k, usually what we call this. This is a big Algebra 2 thing. Do this a lot in Algebra 2. Moving functions to the right and up or left and down, whatever else. Like that. This is the most common one. We should be aware of a couple other things that you can do, though. I'm going to put a kind of a line here. Let's say you have a negative f of x, where you take your original function, take all the outputs, but make them negative. All this is going to do is take any y value that you have and flip it over the x-axis, which means this causes a reflection about the x-axis, sometimes called a vertical reflection, since all the points are moving vertically from where they were to their opposite point. You can do the same trick by using f of negative x, where you plug in the opposite of the number. This causes it to make a reflection about the y-axis, also known as a horizontal reflection, since the point is flipping from one area to the next, like this, horizontally and vertically, like that. Now, there are a couple other ones that'll pop up along the way, but these are the main ones. These are your translations up here. These are your reflections down here. The absolute values will pop up also, and we'll talk about those as we get there. They will depend on where they are and what they do. But let's get into it. So all we have to do in these first 6 problems is describe with words what's going to happen to the graph of f of x. We don't actually need to graph it. In fact, the x squared minus 1 here is a complete dummy. It could be any graph. But if you took f of x and you subtracted 4 from it, the graph would move down 4 spaces. You take all the outputs from x squared minus 1 and subtract 4 more from them, moving the entire graph down 4 spaces. What about f of x minus 4? Well, this time, you basically, if you think about this like a table of values, all this does is when you go to plug in, like, say, 5, for example, instead you plug in 1. So this moves the entire graph 4 spaces to the right, is what happens there. Moved, I guess I should use the word translated, would be the big word. Translated 4 steps to the right. You know, a big thing we got used to doing in AP Calculus is writing out everything in English sentences, since half of your AP Calc test is free response, meaning that you actually have to write stuff and people are going to read it. And they're going to check for specific words along the way. We have lots of time to talk about this. Now, this is going to do two things. This one is going to combine a reflection and a translation. So, number one, it's going to translate 2 steps to the right, or to the left. Remember, the inside of the function works backwards of what you might expect. This is going to cause everything to move 2 steps back in time. It's also going to reflect over the y-axis. Or sorry, x-axis, my fault. It's going to reflect vertically over the x-axis. Down here in number 4, well, we got a multiplier on here too. So I didn't mention the multiplier. I'll mention it right now. I'll talk about what's going to happen here. The plus 3 is going to be the last thing to happen, but the multiplier happens first. So let's talk about what that multiplier does. It's going to cause what's called a vertical stretch. It's going to take every output of f of x. If you want to think order of operations, the first thing that's actually going to happen here is the function is going to run. You're going to put numbers in for x, you're going to get numbers out for y. But once you're done with that, you're going to take those answers and multiply them all by 5. That's going to cause the graph to stretch vertically by a scale of 5. So we say this is a vertical stretch by a scale of 5. It's really tough to define what a scale of 5 means. It's really tough to measure, but we just write it down. It's important to know. And then after that, it's going to translate the stretch version up 3 spaces. So it's been stretched vertically by 5 and then moved up 3 spaces. That's the key. Question 5, f of 2x. Okay, this is going to do the opposite of the vertical stretch. This is going to cause a horizontal stretch because your inputs are all going to get doubled. So this is tricky to think about. If you think about like a table of values, it actually makes a lot of sense. Instead of plugging in the first number, you're going to plug in the second number. Instead of plugging in the second number, you plug in the fourth number. Fourth becomes 8th, 8th becomes 16th, and so on. So what this does, it causes a horizontal stretch by a scale of 2. Oh, actually, no, the more I think about it, not a stretch, it's a compression. Let's see, I'm trying to have a good way to quickly show you this, but it's going to take a lot of work on the calculator. Maybe this is a thing we'll explore in a later topic when we talk about using the calculator for things. But the horizontal compression, I mean, what happens is that when you go, well, here I can show you the table of values. Let's say you have our function was x squared minus 1, so it might be worth making a quick graph of this. So let's go 0, 1, 2, 3, maybe 4, like this. So 0 gives you negative 1, 1 gives you 0, 2 gives you 3, 3 gives you 8, and 4 gives you 15. Just doing the math really quick in my head. Here's the thing. When you go to, if we try to run this function, if I say, hey, what's f of 1, it actually becomes f of 2. And so f of 1, instead of giving me the value for 1, instead gives me 3, because I go to the next point over. So what this does is it causes the 3 to happen not when x is 2, but when x is 1 instead. And this only gets worse and worse as you go. If I try to say, hey, what's f of 2? Well, you go, okay, well, I'm going to multiply 2 by 2 and make f of 4, which is 15. So at x equals 2, you actually get the y value from when x is 4. So it causes all of these points to shrink and push down towards the y-axis. Maybe I'm doing a good job of explaining this. Maybe I'm not. Ugh, I feel like I'm talking too much. So I'm going to move to the next question. Horizontal compression is what's going on there. Now we have an absolute value graph. And notice where the absolute value symbol is. It's at the end of the function. You run the function. You get a bunch of answers. You take those answers and run them through an absolute value. This does nothing to any of the positive answers, but any of the negative function values will flip up above the y-axis. So it's kind of like a reflection, but not quite. So I guess the best way to describe this is with an English sentence. Any portion of the graph, any portion of f of x that is below the x-axis reflects to be above the y-axis, or sorry, x-axis. Again, what's tricky about this is it does not affect any portion of the graph that's positive. Only the negative parts of the graph are affected. We'll get a chance to practice this in just a moment when we look at the graphs. So let's actually do that. The second half of this assignment has a bunch of, it gives you an original function. This is a very, very common thing that we do in calculus. We give you some ridiculous graph of some ridiculous function. In order to give an actual equation for this would be preposterous. This actually wouldn't be too hard. It's actually just 3 straight lines. But a lot of times you just get a graph and you're told, okay, this is f of x. All right, good, we'll go with it. So what we got to do is use our knowledge of how this works to sketch what the following graphs would look like. I think it's important before we start to locate the key points. This is the point -4, 0. This is the point 0, 2. We do have a 0, 0 in there, which is worth mentioning really quick. This point down here is the point 2, -2. And we finally have our last point, which is 3, 0. I should color code those, or maybe give them names. We're going to use these key points to make all of these transformations happen. So for example, the first one tells us to do 2 of f of x, 2 times f of x. Keep in mind, f of x is the y value coming out of the function. So we're going to take those y values and we're going to double all of them. So remember earlier when we noticed that -4, 0 is a key point? That point's still on the graph. That point does not change. However, 0, 2 has been doubled. It is now 0, 4 up there. And 0, 0 doesn't change. Or sorry, I'm a dummy. That's 1, 0. 1, 0 does not change. Notice how the scale of the graph changed. And 2, -2 is now 2, -4. Again, we are doubling the y values. And then 3, 0 is back to where we started. So your graph is going to look something like this. Number 8 tells us to do negative f of x. This takes every y value on this graph and flips it. So we're going to see pretty much the same graph we have up there, only we're going to reverse all the y coordinates. -4, 0 is still here, but now it's 0, -2. 1, 0 is still there, but now it's 2, +2, and 3, 0 is 3, 0. So the graph looks something like this. Looks a little different because they changed the scale on these graphs, but there it is. Now, number 9 is probably the trickiest one, but so far at least. It's going to move this entire graph 1 space to the right. If you need a visual for what that looks like, take, for example, the input in this case of x equals -3. If we were to plug that into this function, this would return the value of f of 4, because we take -3 and subtract 1, which we know to be 0. Which means that on our graph, if you're following the logic train coming out of this, our graph includes the point -3, 0. Which is an explanation as to why every point has been moved 1 space to the right, because we subtracted 1 from it. So now it's -3, 0. Now it's 1, 2. Now it's 2, 0. Now it's 3, -2. And now it's 4, 0. So the graph looks pretty much exactly the same as the graph before it, only everything's been moved 1 space to the right. Number 10 is going to take our key graph and move all of these numbers 2 spaces up. So we take the example graph from before, and we're going to move it up 2 spaces. So -4, 0 is now -4, 2. 0, 2 is now 0, 4. 1, 0 is now 1, 2. 2, -2 is now 2, 0. And 3, 0 is now 3, 2. Everything got moved up 2 spaces. You might notice there's kind of a ghost x-axis where there used to be. Where the x-axis used to be, it's now x equals 2, or y equals 2, rather. Pretty cool. Here's where things get interesting, the absolute value of f of x. We're going to take the graph that we have up above, and we're going to take anything that's negative on it, and we're going to flip it up above the y-axis, x-axis. I always get those two confused. We are not going to touch the entire portion of the graph from -4 all the way to 1. This part of the graph stays exactly the same. Let's draw it right now. -4, 0, 0, 2, 1, 0. This part of the graph stays exactly the same. However, all of the part of the graph that was below the x-axis now has to go above the x-axis. The easiest way to do this is take the point 2, -2, flip it up, and make it 2, +2. Put it right there. So the graph now looks like this if you connect those points. All of the negative stuff became positive. Kind of a different shift, a weird, interesting thing here. And this last one is going to be easily the most confusing. what we're going to do is we're going to take f of negative x. And so we really should think about this maybe as a table of values for a second. So let's take our regular input, then we'll think about the absolute value of that input, and then we'll think about f of the absolute value of that input. And keep in mind, we're talking about f of the original function. We're talking about the original function. So we'll get that in a minute. We have some key points. We have negative 4, 0 to consider. We've got 0 to consider. We have 1 to consider. And we have, what are the other ones I got? 2 and 3. And actually, I want to start with 0, 1, 2, and 3, because those will actually not be affected. Because, honestly, if you're looking at the middle column of our graph, the only one that gets affected is that negative 4 becomes positive 4. These guys all stay the same. In fact, if you're following along and paying attention to that, what that means for you is that the entire right side of the graph is unaffected. 0 is still going to give us 2. 1 is still going to give us 0. 2 is still going to give us negative 2, and 3 is still going to give us 0, because we already know what those answers are. So the entire right side of this graph is unaffected. It's the left side that's going to trip us up. So negative 4, let's think about that. We input negative 4 in the function. The absolute value becomes the positive 4, and now we're thinking about f of positive 4. Now f of positive 4 we actually don't have on this graph. Look at this. F of 4 doesn't exist. There is nothing on the domain of this graph beyond this point. There's nothing over here. So f of negative 4 actually doesn't exist on this graph, DNE. Now let's try, for example, let's try a point we might know. How about negative 1? Well, negative 1 becomes positive 1 when you take the absolute value of it, and we already know that the function value for 1 is 0. What this means for us is that we're going to graph the point negative 1, 0 on this graph, which is right here. I'll do one more, and maybe you might see the pattern that's about to develop. Let's try negative 2, which gives us positive 2, and f of 2, last time I checked, was negative 2. Again, we're seeing that right there. So, again, the point that we're going to graph is the point negative 2, because our input was negative 2, our original input, before we did the absolute value thing. And this actually brought us down here. And what you're starting to see is that we get a reflection over we take the positive parts of the original graph and reflect those over the y-axis into the negative space below. Negative 3 will also give us 0 for the same reason. Negative 3 becomes positive 3, which returns 0 into the function. So we get a graph that looks like this, and there's nothing beyond positive 3. Positive 3 is the end of this graph, so there is nothing. Even though the original graph has negative 4, our doesn't have anything. That's what this graph looks like. It's kind of interesting. It causes a reflection of just the positive parts of the graph back into the negative space on the left. That's an interesting graph. That is the end of this particular topic there. So again, I'll leave these for you to just look at and pause at the end. Again, don't be discouraged by any of this stuff. It's a lot of review. I don't ever want to say that, oh, this is review, you should know it, as if I'm gatekeeping the class. My philosophy is that anybody can do math. Anybody can do calculus. It just takes a little bit of time, and it might take a couple of reps of things too. So give yourself some patience. If you made it to the end of this video, congratulations. I'm so proud of you for taking the class, and I hope you're having a good time this summer. Hope you're enjoying this series of videos I'm making for you, and I will see you in the next one, which I will probably record from home.